Okay, good morning, everyone. So, today will be the last lecture for this course. Today, I'm planning to state the spectral theorem for compact self-adjoint operator. So, before that, let me talk a little bit about yesterday's quiz problem. So, we had this T from L2 to L2 given by T of x1, x2, x3, x4, so on equal to, I think we had x2 minus x1, x4 minus x3, and so on. And we had to find the set of eigenvalues and spectrum. So one thing is that sigma pt, this we have to calculate, and the whole spectrum. So I think part A, many of you could get the eigenvalues, but there also I want to point out some mistakes. And part B, to find the spectrum. In this case, in fact, spectrum and the set of eigenvalues are same, and we get plus minus iota, but you have to give proper arguments why this is the case. So for the first one, you just have to find the eigenvalues, so that you can do just by using the definition. So, so let us try to solve for, let lambda belongs to C, we says that T of x equal to lambda x, then we get x2 minus x1, x4 minus x3, and so on equal to lambda times x1, lambda x2, lambda x3, lambda x4, and so on. So what does this give? This implies x2 is equal to lambda x1. In fact, I can simply write, you see that x2 will be lambda x1, and x1 will be equal to minus lambda x2, and then x4 is x1 is minus lambda x2, x4 is lambda x3, x3 is minus lambda x4, and so on. So that is same thing as if I take x2n, that is equal to lambda times x2n minus 1, and x2n minus 1 is minus lambda times x2n. This is true for all n belonging to natural number. So x2 will be lambda x1, x1 is minus lambda x2, and so on. So if I substitute x2n minus 1 equal to minus lambda x2n, then this implies x2n is equal to minus lambda square times x2n. This is for all n. So this thing is equivalent to 1 minus lambda square times x2n is equal to 0 for all n. So now if 1 plus lambda square is non-zero, if 1 plus lambda square is not equal to 0, that is lambda is not equal to plus or minus iota, then this is non-zero, so x2n has to be 0 for all n. x2n equal to 0 for all n. And because x2n minus 1 is minus lambda x2n, so this will also imply that x2n minus 1 equal to minus lambda x2n. This is also 0 for all n. So this implies the vector x is the 0 vector. So what does this say? This says that lambda equal to, if lambda is not equal to plus minus iota, then it is not an eigenvalue. So therefore, if lambda is not equal to plus minus iota, then lambda is not an eigenvalue of T. But can I say that this implies that plus minus iota are the eigenvalues? I think many of you conclude from this that therefore the set of eigenvalues is plus minus iota. But this is only telling you that if it is not equal to iota or minus iota, then it is not an eigenvalue. But in order to say that plus minus iota is an eigenvalue, you have to find an eigenvector corresponding to that. Then only you can say, right? Because it may be that even iota minus iota, they may not be an eigenvalue. So you have to now see for iota minus iota whether it is an eigenvalue or not. So I think the mistake that you are making is that you are thinking that okay, if it is an if this x is an eigenvector corresponding to lambda, then x has to be non-zero vector. So if we have 1 plus lambda square is equal to 0, then of course we'll get uh, 1 plus lambda square times x2n. This will be 0. So it will satisfy this equation. And then probably you can choose some non-zero, this x2n and then x2n minus 1 also. But one has to be careful, right? Because you have to find a non-zero vector in this space, right? In this space such that it satisfies this equation, right? So you will have to find a vector x which is non-zero and it belongs to L2 such that this happens. Example, see, if I just look at this, you may say that okay, I'll choose the x2n equal to 1 for all n. So all these x2, x4, x6, if you choose it equal to 1, then of course it will satisfy this equation. And in that case, suppose I take lambda equal to iota, then what is x2n minus 1 will be minus iota. So in that case, suppose I take this. So if I take x2n equal to 1, this will imply x2n minus 1 if I take for lambda equal to say iota. x2n minus 1 will be equal to minus iota. But in this case, what is x? X will be equal to minus iota 1, minus iota 1, and so on. But does this, so this will of course satisfy if you find what is t of this, that will give you iota times, t of this x will be equal to iota times x, right? You just see this t of x, that is x2 minus x1 and so on. So x2 will be equal to 1, and then iota 1 iota and so on, which is just iota times this vector. But does it imply that this x is an eigenvector?
It's not in L2.
It's not in L2, right? So, but this x does not belong to L2. So I cannot choose this as an eigenvector, right? So it's not that you choose any non-zero vector and then you will get, right? So you will have to make sure that you can find an eigenvector. But what I can do is the rather than this, I can take uh, say x2 is equal to 1, and then x1 is forced to be equal to minus iota, and then I can take other x to be is 0, right? And x n is equal to 0 for n bigger than equal to 3. Then you see that it satisfies this equation. So x2 will be equal to lambda times x1, and x1 will be equal to minus lambda x2, and then because x3 x4 these are all 0, so it will satisfy these other equation that x4 will be equal to lambda x3, x3 will be equal to minus lambda x4 and so on. So this vector, if I take x is equal to minus iota 1 and then rest are all 0, this is an eigenvector of t corresponding to eigenvalue iota. And similarly, if I take lambda equal to minus iota, then you can take again x2 equal to 1. In that case, x2 will be iota. So if I take x equal to iota 1 and then all rest are 0, this is an eigenvector for eigenvalue minus iota. Right. So this says that hence this set of eigenvalue, if I write, this is equal to iota and minus iota, because we know that nothing else is an eigenvalue and these are indeed eigenvalues, right? So one has to do in the quiz, probably I am not like cutting marks, but to show that something is an eigenvalue, you must find an eigenvector, right? Then only you are sure that okay, that is an eigenvalue. Just because the, you say that other than this there is no eigenvalue doesn't mean that this is an eigenvalue, right? So your argument should be complete. Now the main part is about this second one. Now how do I find spectrum now? So of course we know that sigma of t, this contains sigma pt, which is equal to plus minus iota. So I know that these are in the spectrum, iota and minus iota. But maybe because this is on infinite dimension space, so there may be other eigenvalues also. So we have to, what is sigma t? Sigma t we know is all lambda in C, such that lambda I minus t is not invertible. So this will consist of all lambda where either lambda I minus t is not 1 1 or this is not on 2, right? So this can be written as the one is sigma pt and then union with lambda in C such that lambda I minus t is not on 2. So you should just try to see that when is this onto. So if I look at this lambda I minus t, lambda I minus t of any x, so that will be lambda x1, lambda x2, and minus t of x1, x2. So you will get this is equal to lambda x1 and t of x gives x2. So minus x2 and then lambda x2. And second component was minus x1. So that will become plus x1. And then the other component, it is like repeating like that. So lambda x3 minus x4 and lambda x4 plus x3 and so on. So now we have to see whether this is onto or not. So we take any y and then try to find. So let y equal to y1, y2. This belongs to L2. We want to know whether there exists x such that lambda I minus t of x is equal to y. Right? So for a given lambda, we want to find. So we want to see whether lambda I minus t of x equal to y. Does this has a solution? So here it means that again this vector x has to be in L2. So when that will be true, so this will have a solution. So if we get this lambda x1 minus x2 is equal to y1 and lambda x2 plus x1 is equal to y2, and then the other one is similar pattern we have. So we have to just look at these two equations and then try to solve. So in fact, I can write lambda x2n minus 1 minus x2n is equal to y2n minus 1 and lambda x2n plus x2n minus 1 is equal to y2n. This is true for all n. So here now if you try to solve this, you will see that this is like a system of two equations in two unknowns, right? And if you look at the this coefficient matrix, it is lambda minus 1 and then lambda 1. So its determinant will be, did I write it correctly? Yeah, this is correct, but I should write like this. So next one I'll write as x2n minus 1 plus lambda x2n. So we get lambda square plus 1 as the determinant, right? So if the determinant of this coefficient matrix is 0, then we know that I can find this a vector y such that it has no solution. So, but if the determinant is non-zero, then I can solve this, right? So if this lambda square plus 1 is not equal to 0, then I can solve this and you can find what x2n minus 1 and x2n are. So this is just 2 by 2 system you can solve. You multiply, for example, to find x2n minus 1, you multiply this by lambda and then add it. So you will get lambda y2n minus 1 plus y2n by 1 plus lambda square, and x2n will be equal to, you multiply this by lambda and then subtract. So lambda y2n minus y2n minus 1 by 1 plus lambda square. This again has to be true for all n. Again, you see that just saying this, so it might look like that if lambda square plus 1 is non-zero, see, because for lambda square plus 1 equal to 0, we already know that that is in the spectrum. So we have to only see whether anything else is in the spectrum or not, right? So if lambda square plus 1 is not equal to 0, we want to see whether it is onto or not, right? So if it is onto for every lambda not equal to iota minus iota, then that will mean that it is not in the spectrum. So because it is 1 1 also for that. So but this is not enough, right? Again, you have to make sure that this vector x that you are getting, whether it is in L2 or not, right? So now you have to see whether this is in L2 or not, right? So we need to check if this x given by this. So if I write x1 will be lambda y1 plus y2 by 1 plus lambda square, lambda y1 plus y2 by 1 plus lambda square, and then x2 is lambda y2 minus y1 by 1 plus lambda square, and then the other are similarly lambda y3 plus y4 . If this belongs to L2, for y belonging to L2. So y was given to be in L2, and then if this belongs to L2, then only we know that it is this operator lambda I minus t is onto, right? Otherwise, it will not be onto. So, so that again is not difficult, but you have to know that you need to check this, right? So for this, you have to square this and add. So basically, we need to find summation of this mod of lambda y2n minus 1 plus y2n by mod 1 plus lambda square plus lambda y2n minus y2n minus 1. This actually mod square, and n is equal to 1 to infinity. This will give the sum of the square of the absolute value of this component. So this has to be finite, then only we know that this is in L2. But this you can see by using that summation of mod yn square, that is finite, is given. So how do we do this? So we'll get this. So 1 plus lambda square that I can take out. And then I have summation n equal to 1 to infinity this thing. So if I write this as less than equal to, then I'll get mod lambda square y2n minus 1 square plus mod y2n square plus mod lambda square y2n mod square plus y2n minus 1 square. So this is just by the triangle inequality. And now you see that you are getting the 1 plus mod lambda square again will be common. So this is equal to 1 by 1 plus lambda square mod square. And then I have 1 plus mod lambda square common, and then summation n equal to 1 to infinity. This we know is nothing but the norm of y square. So this is equal to 1 plus mod lambda squared by which we know is finite, okay? Because y is given to be in L2. And of course, we are taking this 1 plus lambda square is non-zero. So this shows that therefore, if lambda is not equal to plus or minus iota, then lambda I minus t is onto. So which implies that this if lambda is not equal to plus minus iota, then lambda does not belong to sigma t. Right? Because it was 1 also because it is not an eigenvalue. So now we get that this is invertible, so therefore it is not an spectrum. So which means that this spectrum is in fact just the eigenvalue. Is this clear?
Sir, here, is it also true that like T is compact? Like, if that is true, then we can say
No,
that the
T is
only.
not compact.
Oh, okay.
You see, what is your operator T? T is equal to x2 minus x1, x4 minus x3, and so on, right? So this cannot be an compact operator, right? In fact, for compact operator, we know that 0 should be in the spectrum,
Right, right, right.
right?
Okay.
But I
Okay.
mean,
So, like, if we
by
find this,
the
then would
calculation we
we
have done,
also show?
0 is not in the spectrum, right? But directly also you can see that this is not compact, right? For example, if you take E1, E2, and so on, that orthonormal basis for L2,
Mhm.
then what is T of E1? T of E1 will give you E2. Sorry,
Minus
T
E2.
of T of E1 will give you uh, 0.
Minus. Uh,
No, minus E2. Yeah, T of E1 is minus E2, and T of E2 will give you E1, and then similarly T of E3. So if you look at this bounded sequence
all right,
En,
right.
then T of En does not have any conversion subsequence, because that will give you just minus E2, E1, minus E4, E3, and so on, right? So that we know cannot have conversion subsequence, because the distance between any two is equal to root 2, right? So therefore this operator is not compact. All right. So this, in fact, this example, if you see, if I take on finite dimension, just from C2 to C2, T of x1, x2 equal to x2 comma minus x1, that we know is that rotation operator, right? And that will have plus minus iota as eigenvalue. That same thing we are getting this, because it can be seen as just the direct sum of like those things on the, if I take two components, and then we get this, right? But here to find the spectrum, you have to see, because this is on infinite dimension, so you cannot directly say that this is, of course there are like other ways to also like I mean, in this case, if you try to calculate the adjoint of T, that is easy to calculate. So T star, if you calculate, you will get T star equal to minus T. And also, if you calculate T star T, that will be identity. So T is actually unitary operator, and it is not self-adjoint. It is like anti, like skew adjoint. So T star equal to minus T, and the T star T equal to T star equal to identity. So, but we did not like say what is the spectrum of unitary operator. If you know those results, then what we know is that for unitary operator, just like for self-adjoint also, I did not prove for spectrum. So what is true is that for self-adjoint operator, spectrum is a subset of real number, and if you look at T star equal to minus T, then it will follow that spectrum of that has to be on the imaginary axis. So it has to be iota times a real number. And for unitary operator, the spectrum can be shown to be a subset of the unit circle. So by using that result, one can see that it has to be on the unit circle and it has to be on the imaginary axis. So that will force that the spectrum is can be only iota and minus iota. But those results we have not done. So I mean, in the exam you should not like use that. Right? But directly doing, whether it is 1 1 or not, whether it is on 2 or not, one can easily calculate this. So I just wanted to point out that you should also see whether these vectors are in the space or not, right? Just like for that left shift operator, I said that if you are not careful, then you might think that every lambda is an eigenvalue, because if you look at one lambda, lambda square, and so on, the image of that will give lambda times that vector. But if you are in the space L2 or L infinity, then you have restriction that lambda cannot be like any number. If mod lambda is bigger than 1, then that vector is not in that space. So therefore, it is not an eigenvalue if lambda is that, right? So right. So I pointed this out so that in the major exam, if you have a question, you should not like make such mistakes. Now, think, yes, any question?
Sir, how you write sigma t as a union of sigma pt and Lambda belonging to C says that lambda I is not onto.
This is just the definition, right? What is sigma t? That lambda I minus t is not invertible. What is the meaning of this not invertible? It is either not 1 1 or not onto, right?
Yes, sir.
And lambda I minus t not 1 1 means what?
It is in sigma pt. Yes, sir.
Right. So it is in sigma pt or in this, right? I mean, I'm not saying this is disjoint union. These can have intersection, right? Okay.
Okay, sir.
Okay. Any other question? So now, okay, I don't have much time, so I'll state this spectral theorem and maybe say a little bit about it, but not prove everything. So, so just like when you study in linear algebra, like if you have any square matrix with complex entries, and suppose it is Hermitian, right? So if we have any Hermitian matrix, then what do you know about it? Yes, can anyone tell any property of Hermitian matrix? So one thing you know about the eigenvalue, right? So what do you know about eigenvalues of Hermitian matrix?
It will be real.
It is always real, right? So one is that thing. Another, what else do you know? So is it always diagonalizable? Okay, I don't know whether in your linear algebra course you did this or not, but you can prove that any Hermitian matrix is always diagonalizable, right? So for real matrix, it is like any real symmetric matrix is diagonalizable, right? And for complex matrix, you need A star equal to A. So, so any Hermitian matrix is diagonalizable, and so you have that spectral decomposition of any operator which is self-adjoint. So similarly, we want to do on Hilbert space also, right? So here, first of all, if we have a general bounded linear operator, we know that the set of eigenvalues, it can be uncountable also. So we cannot like uh, expect that spectral decomposition like we have. So therefore, what we will do for only compact self-adjoint operator, what we can say. So let me write this spectral theorem for compact self-adjoint operators. And using this, you can also write the spectral theorem for compact normal operator. So by using that, any operator, uh, we saw that any operator t can be written as t1 plus iota t2, where t1 and t2 are uh, self-adjoint. So if t is normal, then you can write it as t1 plus I t2, where t1 t2 are self-adjoint, and also t1 and t2 commutes. So t1 t2 will be equal to t2 t1. That is easy to check if it is normal. In fact, that is if and only if t is normal. So and then by using this the theorem that I am going to state for the compact self-adjoint operator, you can write a corresponding thing for compact normal operator also, right? For example, if you have a normal matrix, complex matrix, then that is also diagonalizable. But there, like you cannot say that the eigenvalues are real. It can be complex also. So, but let me just state it for compact self-adjoint operators. So So let T be a compact self-adjoint operator. Compact self-adjoint operator on a Hilbert space H. Then first thing is that T has only, or I should say, T has at most countably many eigenvalues. So this we have already seen that for here we don't even need self-adjoint. For any compact operator, the spectrum we saw has to be countable. So it has countably many eigenvalues. And if we write the distinct non-zero eigenvalues as, so if lambda 1, lambda 2 are the distinct non-zero eigenvalues of T, in fact, because this is self-adjoint, we know that these lambda i's are all real. So these are real numbers. And if I write the distinct eigenvalues to be lambda 1, lambda 2, and so on, then, and if I write Pn to be the projection of this H onto the eigenspace corresponding to lambda n, and Pn is the projection of H onto the eigenspace kernel of lambda n I minus t, then these are distinct eigenvalues. So these projection operators, so if I write Pn Pm, this is equal to 0 equal to Pm Pn if n is not equal to m. Right. So this in fact we know because we know that the eigenvectors corresponding to distinct eigenvalues are orthogonal for self-adjoint operators. So using that you can see that Pn Pm will be, because see what happens, Pn maps into the eigenspace corresponding to lambda n, and Pm will map any vector to the eigenspace corresponding to lambda m. So if I take any vector x in H, then Pm of x will be in kernel of this. So that means that Pm of x is either it is 0 or it will be an eigenvector corresponding to eigenvalue lambda n, and then if you operate Pn on that, then that will give you 0. So this is true. And like we already know that each lambda n belongs to R. And the important thing is that we can decompose this T. So we can write this T is equal to summation lambda n Pn. So this we know what is the meaning of this, because this convergence is in the operator norm. So that means that if I take t minus, if I take the partial sum here n equal to 1 to some k, and then take the norm of that, that goes to 0 as k goes to infinity. So this is the spectral theorem. So what it says is that if I look at the distinct eigenvalues, and then I look at these operators. So this is like projection onto just the eigenspace corresponding to lambda n. Then I can decompose this. So this in finite dimension also we study in linear algebra this spectral theorem. So if I take any t, then I can write t equal to lambda 1 times p1 plus lambda 2 p2 plus lambda k pk, where lambda i's are distinct eigenvalues, and this p1 p2 pk are projection onto the eigenspace corresponding to these distinct eigenvalues. So in fact, I can write from this corollary also that if I take what we also know is that because this is a compact operator, this kernel of lambda n minus lambda n I minus t, these are all finite dimensional. So if I take an orthonormal basis for this kernel, so there will be finitely many vectors there. So what we can write is this is can be written as, like, if I write any t of x, then I can write as summation of lambda n times en, where so for each lambda n there may be some say kn many uh, eigenvectors. So I can write like that. So this again I can write as a series where we will get an orthonormal basis, and the t of x can be written as summation of this eigenvalue times the eigenvector. So that kind of decomposition we can write. So okay, so I'll not go into the detail of the proof, but what we do is, the last time we did one result that if we have any compact self-adjoint operator, then we said that either norm t or minus norm t is an eigenvalue of t, right? So we will use that result. So first what we can do is we can take lambda 1 such that mod lambda 1 is equal to norm t. So we know that for compact self-adjoint operator, we'll get either norm t or minus norm t is an eigenvalue. So we choose lambda 1 such that lambda 1 equal to norm t, so that we can choose an eigenvalue like that. And then we look at this space, which is kernel of lambda 1 I minus t. So what we know is that this is invariant under T. So because any eigenspace is invariant under T. So now what we will look at, we look at the orthogonal complement of this. So initially we take H1 equal to H, and then we take H2 equal to this the orthogonal complement of this, call this to be E1, the eigenspace corresponding to lambda 1, and then we write H2 to be equal to the orthogonal complement of E1. Then you can check that T maps H2 to H2, right? So that is by using that this is self-adjoint. So if I take anything in the orthogonal complement of this, then we know that that is same thing as kernel of lambda n bar I minus t star, but because this is self-adjoint, t star equal to t and lambda n bar equal to lambda n, because lambda n is real. So therefore this uh, T will map the orthogonal complement of this to itself. So then we'll restrict T to that H2. H2 is the orthogonal complement of the kernel of lambda 1 I minus T. And then we will again apply this. So that will again be a compact self-adjoint operator. So again we will find one lambda 2 such that lambda 2 is equal to norm of T2, where T2 is T restricted to that. And then we apply induction. So this way we'll get lambda 1, lambda 2, lambda 3 and so on. And this in fact is such that mod lambda 1 will be bigger than equal to mod lambda 2, bigger than equal to mod lambda 3 and so on. And then we can prove that this T can be written as this summation lambda and Pn. So let me not go into the detail of the proof, but that is the idea. And this is a very important theorem. So I wanted to at least state this. For any compact self-adjoint operator, we can do this. If it is compact normal operator, then we can again write it as T equal to summation lambda and Pn, where these lambda n's are again distinct non-zero eigenvalues. But in this case, this lambda n need not be real. So we'll get the same thing. And to prove that, we can use this theorem by writing T as T1 plus I T2, where T1, T2 are self-adjoint. And then we apply the spectral theorem for T1 and T2 we can do. And then using that, you can see that you can write the spectral theorem for compact normal operator also. If it is not a compact operator, then we cannot write as this infinite sum. In that case also they are like more advanced spectral theorem, but there you will need integral instead of this summation. So that needs the concept of spectral measure. So for general normal operators also there are spectral theorem, but that is beyond the scope of this course. So I think I'll finish the syllabus with this theorem. This theorem, of course, we have not proved it, but at least the statement you know. And so if there are any questions, you can ask. And the quiz 2, you will get the results by today. So you will know your PMT. Quiz 1 and minor, you know your scores, and quiz 2 also you will get today. And then the major exam is on 18. I'll send the detail about the major exam, how it will be conducted and all by email. Does anyone have any quick question? If not, then we can stop.